can do with it from DESI. So as Ignacy said, I just finished my PhD earlier this year. So most of what I'm going to be talking about was done with collaborators in the UK, such as Andrei and Benjamin Joachimi. And now I'm also at Ohio State, also been working with Paul Martini. So let me just jump in. Right, so this is a very brief outline of my presentation. So I'll start with a bit of introduction and background, talking a bit about DESI as well, and then I'll talk about the Lyman-alpha forest as a tracer for large-scale structure. And then the main part of my talk will be this 3 ways that we are planning to, or we had in the past, gain cosmological information from this tracer. So those are baryon acoustic oscillation, the Alcock-Paczynski effect, and redshift phase distortions, and I'll be introducing all of this later on. So talking a bit about DESI, so DESI is already about 1.5 years into the main survey. It's a 5-year survey. It's a large spectroscopic instrument in Arizona in the US. We are very well on track to finishing actually early before the planned 5-year survey. This is just an illustration with the different types of tracers that we are planning to use for cosmology. And as you can see, these vary from low redshift tracers, and this include the bright galaxy survey, where we're just targeting bright galaxies in bright time. So that's when, for example, the moon is up, and it's much harder to observe faint galaxies. The main tracers then include LRGs and ELGs, so luminous red galaxies and emission line galaxies between redshifts roughly 0.5 to 1.8 or so. And that's the main bulk of spectra that DESI will observe. And then finally, the main topic of my talk today is the observations of quasars. So these are DESI will observe quasars all the way from lower redshifts around 0.8 to high redshift around redshift 4. But specifically, what I work on is the Lyman-alpha forest, which appears in the spectra of high redshift quasars between about redshift 2 and redshift 4. So that's the last part in this plot here. So yeah, so also DESI will be about 10 times larger than the current state of the art, that is SDSS. And today I'll talk a bit about forecasts of DESI and what the plans are for DESI and how is it going. But I'll also be talking about some of my work that was done on eBOSS data, and that was also in preparation for DESI. So this is a plot from the final cosmology result paper from eBOSS VR16, just showing some of the main results from SDSS that include both BOSS and eBOSS. So in the top panel, it's showing expansion history constraints, and in the bottom panel, it's showing constraints on the growth rate of cosmic structure. So specifically, and you can see all of the different points from the different tracers. The one that I'm most interested in are the ones here at very high redshift. There's 2 points that BOSS and eBOSS measured. One was from the autocorrelation of Lyman-alpha forest that I'm going to talk about a bit later. And the other one is from the cross-correlation between the Lyman-alpha forest and the quasar distribution. And all of the other points at low redshift, they're from the galaxy distribution using different probes such as LRGs, ELGs, and quasars. So this is how the picture currently looks like. This only includes BOSS and eBOSS. There's of course other surveys, but these are the tightest constraints on the expansion different growth. And before going on, I also want to quickly mention, so why do we want to measure this? So for the expansion history, measuring the expansion history helps us constrain a lot of things. Mostly the main thing that our survey is also named after is of course dark energy. But there's also, for example, curvature, neutrino mass, and so on. And then growth, we're measuring this quantity as by 8, and that helps us constrain different theories of modified gravity. But there's also this ongoing sigma extension in cosmology that also DESI and eBOSS has put constraints on, and we're trying to figure out if different measurements from different instruments are indeed in tension or is just a statistical fluke. So improving results will tell us if our current models work or not. So that was the picture with BOSS and eBOSS, and then this is a forecast for DESI. This is just an expansion constraint. It's showing a slightly different constant, a slightly different quantity, but it's essentially just the expansion history. So you see how many points DESI is forecasted to measure, and it's well on track to delivering this. So this includes the different points are from the different tracers. These ones at very low redshift are from the Bright Galaxy Survey, and then we have mostly from LRGs, and then ELGs all the way to about redshift 1.8, and then here Lyman-alpha for it takes over, and we get this constraint all the way to about redshift 4. So you can see that with especially at the higher redshift, we're hoping to go from those 2 data points to hopefully a much better coverage of this expansion history. So one question is, why do we even want that many points? Why do we need to measure the expansion history all the way? Why don't we just put 1 point here, 1 point there, and that's enough? So this plot is very nice for illustrating that. So when we're measuring this expansion rate at different redshifts, and you're looking at how that translates into constraints on cosmological parameters, because the components of the universe evolve, and specifically, for example, the ratio between the amount of matter and the amount of dark energy in the universe evolves, constraints at different redshifts, so more distant in time, will give you different angles in this type of panel. So here, I'm just focusing on one type of constraint. This is flat lambda CDM for the simplest model. And in this case, our measurements constrain the fraction of matter in the universe. And then there's this degenerate combination of the Hubble constant, and RD is the size of BAO that I'm going to talk about in a bit. But the point here is that you can see that as the probe goes higher and higher redshift, the angle of this measurement changes. And that means that when you combine measurements from very different redshifts, that helps you really get very tight constraints. Now, of course, this is flat lambda CDM, so sure you ask, why do we care about the value of omega matter very precisely? But this is just a simple plot to show you how this works, but it also applies to all of the extensions that we might want to measure. For example, the equation of state of dark energy, or curvature, or neutrino mass, and so on. So the principle of combining measurements at different redshifts in order to get the tightest possible constraints and break degeneracy is sort of what we're trying to go after. And this is specifically showing here, especially in the past, Lyman-alpha has been very, very useful because there haven't been many measurements at high redshift. And using Lyman-alpha as an anchor for the very, very precise measurements of galaxies, but at low redshift, has been very useful in delivering very good cosmological constraints. Right, so that was just a rough introduction. I will now talk a little bit about the Lyman-alpha forest as a tracer of large-scale structure. There's this very nice animation that was done by Andrei at UCL. Just shows that as light from a background source goes to the universe, when it hits a cloud of neutral hydrogen, this Lyman-alpha line was redshifted to some other value, and when it hits a hydrogen cloud, if it hits a hydrogen cloud, then it will cause some absorption. So as you go, as the light progressively comes towards us, it gets redshifted more and more, and then in this way you have this forest of absorption lines that are essentially tracing the neutral hydrogen between you and that background source, right? But this is just one case, and the power of our analysis comes from having many of these quasars. So this is just an example quasar from eBOSS. It's actually a very nice quasar. You have very high noise, and you can see the main the main regions that we use in our analysis. So we have the Lyman-alpha peak here and the Lyman-beta peak. So the main region that we use is this Lyman-alpha region between the Lyman-alpha and the Lyman-beta peak. And we use the absorption in this region. We also use the Lyman-beta region that is to the left of the Lyman-beta peak. However, this has a much lower signal to noise, so I won't be really talking about this. I just wanted to mention it. The main tracer is this Lyman-alpha region. Right, so once you have this type of spectrum, you arrive at one of the first challenges and one of the most important challenges, which is the fact that you don't know where the quasar continuum is, right? You have this spectrum and you don't know where the continuum is, so you don't know exactly how much absorption there is at this redshift. So usually in cosmology, we work with this overdensity field. And here for Lyman-alpha, that means you take the flux, and then we're supposed to divide it by the quasar continuum, and then this quantity, which is essentially the global mean flux in the universe, such that you get this overdensity field that you can then use the statistical solve for cosmology. The problem is, like I said, we don't know the quasar continuum, we don't know the global mean flux. And so what we do and what we have done so far is that we have to pick this product from our data. So essentially, we have some form of template and you pick it from the data. Now, why this is a big problem is because this forest data, of course, traces the structure in the universe. So, for example, if it happens that this quasar goes to a region that has more structure, that will mean more absorption. So then you will pick a lower product for this thing, even though they are not representative of the whole. So essentially, you're making a mistake when you're picking. And what that means is that will give you a distortion later on in the correlation function that I'm going to talk about. So the fact that we don't know the two quasar continuum is one of the main challenges. There are ways that people are currently looking into to, for example, use the red side of the Lyman-alpha peak to predict blue side, and that works moderately well, but it hasn't really been used for technology in the last few years. This is the way we use. So, and I'm going to touch on this later on because this is one of the main limitations in the cosmology that we can get out of the Lyman-alpha forest. Also, if anyone is interested in solving this problem, this is one of the main problems in Lyman-alpha. So a lot of work would be very useful here. Right. So as I was saying, we don't just use one for it. We use many for it. So in the last eBOSS analysis, we had something like 250,000 Lyman-alpha for it. With DESI, the current forecasts are around 900,000 for it after the 5-year DESI survey. And what we do is we cross-correlate absorption flux between different forests. We never do it in the same forest because of that distortion problem. So here I'm just illustrating the path to two quasars, and you have some gas clouds that cause some absorption, and that gives you one of your pixels in the spectrum. And what we do is we assume some fiducial cosmology. This is something we have to do, and I'll come back to that later, in order to define co-moving coordinate grids. So we want to compute how far away the two pixels are in co-moving coordinates. And once we do that, we assign this correlation to one of these points in this grid. So this is a grid of co-moving coordinates along the line of sight and across the line of sight, and this is showing the Lyman-alpha autocorrelation from the entire eBOSS data set. So you can see it's quite noisy. There's a lot of features. I'll talk about them in a second. But the point is that the signal that we're trying to get, at this stage at least, it's quite hard to see. What makes it slightly easier if I also show you a model for this Lyman-alpha correlation, and now you sort of can see a little bit of a signal here, the VAO that I'm going to talk about. which is here appears as a circle at about 100 megaparsecs divided by 8. So that's one of the main things that we're trying to measure, which is exactly the position of this circle. But let me make it easier to see what's going on. So normally in a lot of our papers, we usually don't plot this type of plot because you can see it's really hard to get a lot of information out of them. We usually compress our data into this wedge. So the way this works, here I'm just plotting a simple model. And what we do is we define this sort of like pizza wedges, and then we compress all of this information in one wedge as a function of this isotropic separation. And that gives you the dark blue wedge over there. And then you do the same in multiple wedges, and now you can see a bit more information in there that it's much more useful to understand what's going on. And you can also directly compare the data with the model. But keep in mind that when we actually feed the model to data, we actually do it in this space. So features here can be a bit misleading, but it's much nicer to understand what's going on.
How do you go from the left to the right?
Right. So this is like a 2D grid with beams that are perpendicular, and you're just counting. You're essentially defining isotropic shells this way, and then you're counting all of the beams in each shell, and you're collapsing all of those. You're compressing into one data point, and that gives you one data point here. Right, and if you have enough of these shells, I think here it's about maybe 50 points. So you can imagine in each of these wedges you have 50 shells going like this.
Are you averaging all the points in the wedge? In the, like, you draw an arc at like 25 megaparsecs.
Yeah.
And then you average them, and that gives you 1 point there at 25.
Yes, exactly. That gives you 1 point at 25 in this wedge.
Okay.
Yeah. Yeah.
Maybe a question the line that I think the lines of all lines that we draw in there, are they complete with the box exactly the same with quasar position, or we can completely
So here I'm plotting the model is the actual fitted model to the data, and the way that the model is fitted is we use a template approach where we start with a template power spectrum, and then we introduce all of the Lyman-alpha modeling, like a Kaiser model with a bias theta and a lot of other free parameters for all of the contaminants, and we fit all of those parameters to the data. So that's actually the best model to that data, and it's on the data, nothing to do with box.
Nothing to do with box.
Not
the
the
line. Okay, what I'm wondering is, so you could compute the model in order to fit by the averaging vertical parts.
Right.
Assuming the new units or using the actual quasar lines of sight. So you may not exactly see anything out of the.
Right. Yeah.
So I'm not sure now.
So right. So there's many different ways to do it actually. To measure the correlation in different things. So what we do is we just go to this to each pixel. We have right ascension and declination for each quasar, and then we have a redshift for each pixel, and it's just like simple geometry from the plot, and we compute the R parallel and R transverse, and that gives us the coordination. So that's the data that we work with. The other part was just a compression for plotting purposes. We don't actually fit in that space. But this is just one way of doing it. For example, with galaxies, you could do multiples and so on, or you could define different types of beams. Here we use 4 megaparsec beams in our parallel transverse. You could define the beams in isotropic separation and mu, and do logarithmic beams. This is just a choice that we've been going with. And the main reason we've been going with this is because it's in this space, it's the easiest to model some of the contaminants, especially the distortion that I was talking about. we know how to do it here, and it would be quite tricky to do it in other spaces. And the same with the metal lines I'll talk about in a second. Right, so yeah, so here you can see very nicely the PAO peak that we're trying to measure around 100 megaparsec. So in Baryon Oscillation analysis, all we care about is the position of the peak in isotropic coordinates or anisotropically, but we're essentially just gaining cosmological information from this, and we're marginalizing or ignoring the cosmological information in the rest of the correlation function. Before I go on, I also wanted to quickly touch on some of the contaminants. So here you see that the model I'm plotting, I'm not sure how well you can see it. I need to change the colors in the future. So you see that it's quite different between the model there and the model here. So the difference is the distortion that I was talking about. It's exactly the same model, but this one has the distortion because when we see the real data, we have to use the distortion. But of course, because we create the model, I can choose to take it out. So here I'm taking out the distortion because you can see some of the features much nicer. You can better see the PO peak maybe a little bit here. But more importantly, you can see this peak along the line of sight. So this is a Lyman-alpha specific contaminant. These are metal peaks. And why these appear is because when we have that forest, we assume that all of the absorption that happens there is from Lyman-alpha absorption, right? But of course, that's wrong. There's also metal in the intergalactic medium that will also cause a little bit of absorption here and there. And the problem is when we compute the redshift of that absorption, assuming it's Lyman-alpha, but it's actually some metal, we get the redshift wrong, very wrong, right? So instead of it being a gas cloud, neutral hydrogen cloud here, it's actually some metal absorption at a completely different part of the universe. So what that means is that when we're assigning the correlation into beams, we're assigning them in the wrong beam. So these peaks that you see here, they're essentially the cross correlation between metals and Lyman-alpha that's supposed to be here at very small separations because things that are very close by are very correlated to each other, but we wrongly assign them to different separations. And this one is a worrying one for PAO because it happens to be right on top of the PAO peak, and it's partly why it's right along the line such a strong PAO peak. Part of it is that metal line. So that's something we always have to worry about and be careful with and study with mocks and so on. Yeah. It spills over. Yeah, that's the problem. So so usually we also, when we do robustness tests and so on, we try removing some of the first columns here. Yeah. Yeah. So the problem is that this is essentially, you can think of it as taking the cross correlation across the line of sight and moving it at the wrong RP. So it's not just this, it also goes like this, as this would do, right? And the other problem with it is if you're cutting the first few columns, we have this model for this method, and that's the part that gives us the most information to constrain those three parameters. So you're cutting that, and then you can't constrain the model. But also the idea is that would make it more robust. So it's it's a tough problem. Right. So I was talking about the Lyman-alpha oscillation so far, but we also work with the cross correlation between the Lyman-alpha distribution and the quasar distribution. And this is what I'm plotting here: the data on the left and the model on the right. And you can see that this is not just one square, it goes, are parallel, those has negative and positive values. And this is because we distinguish between forest pixels that are in front of the quasar we're correlating with or behind the quasar that we're correlating. And that means that this is asymmetric along the line of sight. But that's fine, we just compute it like this. It just means that it's twice as many data points. We have a model and we see the model. So from now on, whenever I talk about, everything I will talk about will include both autocorrelation and cross-correlation combined. And doing a joint analysis of the two is very advantageous because it helps you constrain a lot of those free parameters that we have for all of the contaminants. So that's why usually we work with the two. Right, so let me move on to Baryon acoustic oscillation. Right, so these are a very nice illustration, very old now, by Daniel Eisenstein from when BAO was first discovered in 2005. So these are acoustic waves in the primordial plasma that traveled when the photon field and the baryon field were coupled. And at some point when the universe cooled off, the photons were free to travel. And this baryon acoustic oscillations remain frozen both in the distribution of radiation, and we can measure that in the CMB, and in the distribution of matter, which then evolved into the galaxies that we observe today. But of course, things are not as nice as the plot on the left. It's more like the plot on the right, where you have multiple of these peaks. So it's a signal that you can only see in the statistics from a large data set. So this is again showing how that peak evolves when the gas and the photons are coupled, and when the photons disconnect and the gas still retains that peak. So this has been measured for a very long time now with galaxies at lower redshift in both the correlation function and this type of peak, and also in the core spectrum as a WIGO. But of course, I was talking about Lyman-alpha forest. So let me talk a little bit about how we want to do that with DESI. So measuring baryon acoustic oscillation from the Lyman-alpha forest is what we call a key project in DESI, at least for the first year of data. And it's one of the things that were in the core of the project when it was being designed. So what we do is, like I said before, in order to fit those correlation functions, usually we use a template. And this template is decomposed into a peak and a smooth component. So essentially, we have a template for how we think this is supposed to look like. And then we take this part, which is just a peak, and we separate it from the rest, because that allows us to take that template for the peak and then move it or shift it left and right in order to see the real data without affecting the rest of the correlation function. So that's what we do, and we have two parameters, alpha parallel and alpha perpendicular, that shift the BO peak along and across the line of sight. And here I'm just using the equations. So these are just distances, and it tells you how to translate this measurement that we make of these two parameters into cosmology. Right, so this is showing in blue the measurement from the last eBOSS BO analysis, eBOSS DR16. So that's a real measurement, and the red is just a forecast for Lyman-alpha BAO from the entirety of DESI. So this is just showing you the type of improvement that we're hoping to have with DESI versus the current state of the art. And here I want to talk about this because it will be relevant later. So this is the, when we measure BAO in flat lambda CDM, this is the parameter space where we get information in. So the matter density and this combination of the Hubble constant and RD, where RD is that the size of those BAO that has remained frozen since the early universe. Right, so quick status update on DESI. It's been going very well. We have finished collecting the first year of data in June 2022, and we are now working on analyzing the data. This here I'm showing the plot with the Lyman-alpha autocorrelation from DESI. This is just using the survey validation data and the first 2 months of data. So it's not quite as good as eBOSS yet, but the year 1 data that we already have and are working on is already better than eBOSS. And here, this is of course blinded because, like I said, EAO is a key project, and we're blinding everything that is a key project in DESI. Right. So Lyman-alpha is big funny. Yeah. So in galaxies, the catalogs, the galaxies are actually blinded. So they're modified in such a way that the cosmological results are not a real one. That is the problem with Lyman-alpha because of the metal, right? The metal, if you're doing something to the catalog, you're also doing something to the metals. And the problem is we know exactly where the metal bits should be. So if you see them in the wrong spot, you instantly know what's the cosmology shift that has been done to this data. So we couldn't do what was done, what was being done with galaxies. So here it's a very simple blinding where we went and we took a best model from eBOSS, a template, and then we shifted BAO in some random way. So now we have a second template, and then the difference between them gives you a template, a blinding template that is automatically applied to all of the data. So essentially, all of the points around the BAO peak are shifted in a coherent way such that BAO is shifted either left or right. So we don't know the real result. So yeah, and right now we're trying to decide if we want to unblind as an exercise for these early data papers or not. And it's still not clear because we are not planning to measure BAO. Like I said, this is not as good as eBOSS. So it's mostly about us understanding the data and preparing for the main analysis on year one. Right. So that was BAO, but like I said, we have this beautiful correlation, and BAO is only dealing with cosmological information from the peak, and we're ignoring everything else. So what I spent my last year and a half on basically was try to gain cosmological information from the rest of this correlation, so statistics from the peak areas, both at small scale and at large scale. So that's what I'm going to talk about next. And there's two main ways, two main paths for gaining cosmology out of those that have been used a lot in the past with galaxies, which is the Alcock-Paczynski effect and redshift phase distortion. So this is just showing what has been done with BOSS and eBOSS. And here I'm using the quasar autocorrelation as a proxy for all of the other correlations for galaxies at low redshift. So there's two types of analysis being done: a BAO analysis, where you're just measuring the position of the BAO, and what we call a full shape analysis that includes both BAO but also this other source of information, which is redshift phase distortion and Alcock-Paczynski effect. Note that when I say full shape, I mean we are gaining cosmology from the full shape. It doesn't mean we are fitting cosmology directly to the full shape. This is something that in the cosmology community often gets confused. On the other hand, with Lyman-alpha up here, you see that we've only done BAO and eBOSS for the last almost 10 years now. It's only been BAO. So I've been working on adding Lyman-alpha full shape, and in this first analysis, we just focus on the Alcock-Paczynski effect that I'm going to be introducing in a second. With DESI later on, I will touch on redshift phase distortions, which we're also planning to measure from the first year of DESI. Right. So the Alcock-Paczynski effect is actually something quite nice that happened in our analysis process. So when we measure those spectra, we are measuring angles, so the position of the quasar on the sky, and we are measuring redshift. So for each of those pixels, we have some redshift. So when you're cross-correlating to pixels, you have a difference in angle, the delta theta, and a difference in redshift delta z. However, like I said, we're actually computing our correlation function on grids of co-moving coordinates, orthogonal and transverse, and you need a fiducial cosmology to do that. So you need to assume a certain Baryon expansion in order to make the transformation. Now, of course, you don't know what the true cosmology is. That's the whole point of doing this. So if there's a difference between what you assume and the true cosmology, that will introduce an entropy in what you measure. So that's just the difference between what you measure along the line of sight versus across the line of sight. Here, because now I'm talking about the anisotropy being introduced for the whole correlation, not just the BAO peak, instead of alpha parallel alpha perpendicular, I'm talking about Q parallel Q perpendicular. And if we want to constrain this anisotropy, we redefine the parameterization as this phi parameter, which is just the ratio between the two. That measures the anisotropy. And then we also have the alpha parameter, which is basically isotropic scale. But here I'm talking about the whole correlation. So you can think of you have a template and you're shifting the coordinates of that template altogether, right? Either isotropically or anisotropically. And again, this is just telling you how to relate cosmology. Right, so I want to show you a little bit about how that looks in practice. So on the left is the phi parameter, so anisotropy, and on the right is isotropy. And here I'm just playing with the peak component, right? So I was telling you before, we have the template, we decompose the peak and the smooth component, and this is showing you what happens when you change the value of the phi parameter, lower value on the left, higher value on the right, just for that peak component. So you can see it sort of either stretches along the line of sight and compresses across the line of sight, or the other way around. Whereas if you change the value of alpha, it grows or shrinks isotropically. So that's the peak, and that's what we measure with BAO. What we want to do is something more like this. So we want to gain cosmology from the rest of the correlation function. And that means changing also the smooth component, and that's what I'm doing here. So you can see the BAO peak in this case is fixed at the same distance. And I'm using the two parameters to change the rest of the correlation. And then you can also do it with both of them at the same time, so changing the entire correlation, like I was saying before. And
can you remind what the difference between phi p and phi s?
Right, so p just means peak. It's just shifting the position of this circle here, right? Whereas s means smooth, so it's changing the coordinates of the smooth component, right? So that means everything but the peak.
And can you go back to the slide where you define? No,
yeah.
So you're defining a phi for both the peak and the peak.
Right. Yeah. So we have two sets of these. We have a phi p and a phi s, and an alpha p and an alpha s. So let me go back here. I think that's easier. So essentially, what we do is we think of this line as a template, and we have this part, which is BAO, and we can shift that left and right independently. And then we have the rest of it, which we call the smooth component, and then we can shift that left and right separately from each other. Ultimately, you want to get all of the cosmology that's there. That's why the last plot that I showed was changing both of them. So ultimately, you want to change both of them. This decomposition is just a nice thing because it allows you to isolate the BAO measurement from the other measurement. And that's because BAO is more robust in general, and we've been doing it for many years now, whereas gaining cosmology from the rest, it's very new, so we wanted to isolate it at first, try to understand all of how it interacts with all of the contaminants and so on. But ultimately, when we actually present cosmology results, it's from everything combined. Right, so what we did is we started with the eBOSS data, and this was about a year and a half ago now. That was when DESI was very, very early. So we wanted to first try to do this type of analysis on existing data that we understand very well as a precursor to applying this method to DESI. So before we did this, the analysis on real data, we had to validate this type of measurement with MOCs. So we used a set of 100 eBOSS MOCs. These were created for the DR16 Lyman-alpha analysis. These are very simple MOCs. They're just a Gaussian field where the quasars are just drawn from the log normal distribution. The main issue with making Lyman-alpha MOCs is that you need very, very high resolution, but also you need the boxes to be huge in order to simulate the large volumes that we have at high redshift. And these MOCs do include all of the major contaminants. So they do model that distortion effect I was talking about. They also include metals, then Lyman-alpha systems, and so on. So this is showing the data points are the stack from the correlations in those 100 eBOSS MOCs. So we have 100 eBOSS MOCs, we compute the correlations in all of them, and then we stack all of it together. And this gives us very, very, very precise measurement of the correlations in the MOC. And then we fit it with the model. And I'm also showing the shaded region, that the error bars from eBOSS. So it's sort of showing you what the expected uncertainty, the real uncertainty is from eBOSS, whereas the actual error bars you see on data points are very small because the technical is small. So the point of this plot is to show that the model works quite well, especially relative to the error bars of eBOSS. We'll have to do, of course, something like this for that in the future, but for eBOSS, it works quite well. There's a few points where it goes slightly outside, but it's still within the ones in our region of eBOSS. So once we have the fact, we can also feed these parameters. And here we want to recover the value 1. That tells us that we recovered the same cosmology that was used to create the model. And you can see that in all of these cases, we recover the value of 1. So that means that we are able to recover unbiased constraints of these parameters. And here I'm doing the separation between the P component and the smooth component. And then I also have this alpha, which is the isotropic scale of BAO. But that's our main concern is with this bias. That's what new. The other two, they've been measured before in BAO analysis. So this is just a zooming of just phi and showing in blue the measurement on the BAO peak. So because Alcock-Paczynski changes the entire correlation, you can also detect in BAO, and that's the fact. We just care about the part from the smooth component here, which is the red. And then the black is the combination of the two. And the whole point here is that they're all consistent with 1, which is exactly what we are hoping for. So that means that we are able to model well all of the contaminants that we put in the mod, and they don't bias our result. I'll keep this and this. Right, so once we had the measurements on the mods, we moved on to the data, and here I'm showing the real eBOSS data with the real best fit on the left for the Lyman-alpha autocorrelation, and on the right for the cross correlation. From our analysis on mods, we decided to cut this part out, so we're not actually fitting the very small scales, and that's because we know we can't model the small scales very well, and we found systematic biases in the model. So we're only gaining information from the large scale, about 25 megaparsec divided by h.
On the left, on right, the BAO, or you put them all together? The figures that are different figures.
So here we put all of them together, right? But we know most of our constraining power is actually from the small scale. So that was actually the next slide. So we've done a series of robustness tests where we took the model and we changed different parts of it, and specifically we focused on what couldn't be tested with mocks, either because the mocks were too simplistic in their treatment of large-scale structure, or they didn't include some of the contaminants are maybe not the most important, but it's still good to test for. So we've done a series of changes to the model and then remeasured the value and started plotting the difference between the baseline, so that's the main model I've shown before, and whatever happened when I made that change. And if our measurement is very robust, we expect all of them to be consistent with each other. And most of them are. The only slight outlier is in this test here. And this specifically has to do with the cross correlation, and it's how we model the redshift errors of the quasars. So obviously we have redshift errors in the quasars, and they have quite a complicated model. And so far in bioanalysis, and what we've done here is use a simple, either like a Gaussian spread for those redshift errors or Lorentzian model, and in the baseline we use the Lorentzian. But it's been done for many years now that we also test the Gaussian and see what happens. And here you see about the upper sigma shift in that case for the Gaussian, which just indicates that that's probably one of the most important parts that we need to look further into and try to understand much better. However, for this analysis, we know that the Lorentzian one is the more realistic than the Gaussian because there's quite a complex shape. So we decided to in the baseline to go with the Lorentzian instead of the Gaussian. Right, so now onto the result. So this is the Alcock-Paczynski measurement from BAO, and this has been done in the past by eBOSS and eBOSS. One thing I wanted to note here is, in this case, one means Planck, right? So we use the template and the physical cosmology based on Planck. So one is the Planck cosmology, and already the BAO measurements in the past, both in eBOSS, they've been low. So there used to be about a 2.5 sigma tension. Now with ER16 it's about 1.5, and it's been going down. So it looks like maybe it was just statistical, but interestingly, our measurement is actually high. So the red line is the measurement of the smooth component, and the black is from the entirety of the correlation. And you see that it's on the high side of Planck. They're both within 2 sigma of Planck. I mean, all three constraints that you see there. But of course, one worry that we have is if the blue and the red are in tension, because the black is sort of the combination of the two. And of course, if you have two measurements in tension, it's not the best of idea to combine them. So we did the blind analysis, all of this, before we actually saw the results, all of this was blinded. And we made a decision tree for what we would do when we unblind, depending on the levels of tensions that we see. And we decided that if the tension is above 3 sigma, then we would talk about it, but we would not derive any cosmology from it. This being the first such analysis, just probably means that we need more work. If it's below 2 sigma, then it's fine. And if it's between 2 and 3 sigma, we'll go back and try to think about what happened, but we'll still do cosmology. And it just happened to be a 2.3 sigma. So we spent a few more months looking into other things that could explain this, and we didn't come up with anything new. So it's been a fun, interesting experience, and trying to then decide if 2.3 sigma is enough or not. Yeah. Yeah.
We can get reminded about that what is phi is.
Right.
Phi S, you have phi B, phi P, right?
Yeah.
And here,
so blue is phi B, red is phi F.
the one is the ratio.
Yeah. Of the alpha transverse by alpha parallel. So it's essentially how much you rescale across the line of sight versus how much you rescale along the line of sight.
So then, that's what you can measure with Alcock-Paczynski.
Yeah.
The BAO peak itself. When you do the ratio of the two, it gives you this.
Yeah. So the blue is just from the BAO. So it's Alcock-Paczynski in the BAO peak.
Yeah.
And then the red is Alcock-Paczynski in the rest of the correlation function. Yeah.
But so, okay. You say that the word was 2.3 sigma, but I actually here, yeah, just looking at the two probability curves, they're like not so unlikely.
Right. Yeah.
But at the same time, so then, from the BAO peak, you also get the product, right? The alpha.
Alpha. Yeah.
And so that then. Well, that's of course
you match it with the cosmology, you can't map it into a file. So in order to get the cosmology, you can combine the ratio.
So in the end, we get cosmology from this black one, which is Alcock-Paczynski from the blue, and from that alpha peak. So we still need the isotropic BAO measure.
So it's very interesting to get completely alternative measurement. It goes to the other side, so
right.
The consistently can be part.
But also the 2 sigma are to be the Planck, right? Or are the blue versus the red?
Blue versus red is 2.3 sigma. Blue versus Planck is 1.6 here, and red versus Planck is 1.9. So both of them are within 2 sigma of Planck.
Ultimately, 1 point, like sigma of what? The combined measurement, or?
And then, so sigma just means the uncertainty. So this is like the posterior. So 1 sigma would be 68% of the area under this curve. Okay. So 1 sigma would be, I think, roughly here. 2 sigma would be something like that. right? I'm just saying one is within 2 sigma of where the central line is, right? And usually we use this, in this case, they're all Gaussian, so we can talk about, we don't have to worry about anything complex. And we talk about this when we're talking about tension, because like I said before, if you have things in tension, it's not a good idea to combine them. You should first go back and understand what's going on. And why we were so careful here is because this is the first type of analysis and we have a lot of contaminants to worry about. And it wasn't, when we started this project, it wasn't even clear that we could do this measurement, right? It wasn't clear that we could, that there wasn't some contaminant or multiple ones that would give you some huge systematic bias that you can't. That's why we put it very carefully.
I think if I was doing the one back to,
right.
This robustness plot with all the bars. And
yes.
Let's say, let me marginalize over this extra uncertainty. This
yes.
increases my error to 30% of a sigma, and now it's below 2 sigma, and also when you combine that, if I want to.
Right. So we are actually thinking about something like that. The main worry that we had is that these are completely arbitrary at this point. Like this set of things were just what we came up with, right? And actually the last one we added after we got the referee report. It's something the referee mentioned that would be interesting to see, and then we added it, right? And we thank the referee, of course, because we didn't think of it in the first place. So this is a bit arbitrary, so that's why we're a bit worried about doing something like that. We were thinking for a while if we should increase the error bar because of this shift with this one. The change would have been incredibly small. With just that one, it would have been, instead of the error bar is 2% on this pi, and it would have been 2.2%. So it's a very, very small change. No, so it's a very small change. And again, so here what we went with is we know that the Gaussian one is definitely a very, very rough approximation. The Lorentzian one, even the Lorentzian one is an approximation, but we know it's better. Ideally, with DESI, we want to have a more complex model, and I know already with the quasar autocorrelation for galaxies, there's more complex modeling to do with the modeling fingers of God and the redshift errors. Whereas here we just have this one term.
So one question. So these results are already combining Lyman-alpha oral plus Lyman-alpha.
Yes. Yes. So one of the issues we had was initially we were planning to also look at auto and cross separately. The main issue is the cross. You have 2 quasar terms, one from the Lyman-alpha and one from the quasars. So you have like a biased Lyman-alpha, biased quasar, and then a beta Lyman-alpha, beta quasar, and you can't tell them apart. Like the system is fully degenerate. So what was done, for example, in bioanalysis was if you want to fit cross independently, you first fit the combination, you get the best fit, and then you fit some of those parameters to the best fit, which is very suboptimal when those things are correlated with your signal, right? So you don't want to do something like that. So in the end, we decided not to look into that too much because we know the system is just very degenerate. Hopefully with DESI we'll come up with better ways to deal with that, but yeah. Right, so let me quickly go about some of the cosmology results. So like I said, we gained cosmology from that pi parameter, Alcock-Paczynski, and then from the isotropic BO scale. So in this plot, the isotropic BO scale basically measured a completely degenerate banana between omega matter and H naught RT. And in order to actually get a constraint, you need Alcock-Paczynski. So in flat lambda CDM, Alcock-Paczynski translates directly into a measurement of omega matter. So it's putting an omega matter constraint, right? So you combine the isotropic peak with omega matter constraint, and that gives you some polyp or banana in this case, I guess, for in this plane. So here I'm just showing for now the Lyman-alpha PO, and then the other LRG will shape result in blue, and that's because that's the best constraint from BOSS and eBOSS, that's the LRG constraint. And because we haven't changed the isotropic measurement, the thickness of this hasn't improved, but what has improved is our measurement of omega matters. So you see that this red contour is now much shorter than the gray one. And it has, of course, picked up because exactly that shift that we saw previously. And of course, like I said at the beginning, the idea is you want to combine things at low redshift and at low redshift and high redshift in order to get the tightest possible constraints. And if in this case, we also want to measure the Hubble constant, and there's this technique that's been used for a long time now, which is to combine this type of BAO and Alcock-Paczynski measurement with constraint on the baryon density from Big Bang nuclear synthesis. And that allows you to break this degeneracy and actually constrain H0. And what was really cool in this case was that with just Lyman-alpha, which the red contour here, we get a really good constraint on H0, and that without combining with anything at lower redshift. Interestingly, it's on the low side of Planck, like 3.2 plus minus 2.4. But it's still consistent with Planck and in about 3.6 sigma tension with the distance length of result. I haven't gotten any angry emails from Andrei. Okay.
But this is for now, it's only redshift.
Right. This is, yeah, the interesting, yeah, the BDM constraints also come from about redshift 2 to 3 measurements, and our constraints are between redshift 2.2 to 3. So it's all right. Yeah. Yeah. You need to assume. Yeah. Yeah, exactly. You need to assume the early physics to do. Yes. So it's exactly the same. So hopefully, if there's a solution in the future, everything just works. We'll see.
Of the BAO one.
Of the BAO, yes. So
yeah, of the BAO, but for the Alcock-Paczynski,
right.
you need to know that
Yeah.
so you assume the master transfer function, which is a redshift 1000.
Yeah.
But that doesn't affect very much. Yeah.
Yeah, but the AP doesn't give you 8.
There's a small correlation though between so when we have that alpha and pi measurement, there's a small correlation between them. So that's why, for example, if you look at so the alpha p measures this thickness here basically, and you see it slightly shifted between the red and the gray. That's because there's a small correlation, and the full shape constraint is so much shifted that it shifts slightly the alpha as well. So I think if the early universe is different, it would shift in this plane. So yeah, yeah.
Yes, so
There's
that's
nothing
why
you can do.
much down to the small scale.
Right.
So different physics in the reality, but size
Yeah.
with respect to the BAO in different ways.
Right. Yeah. Yeah. So we know most of our information comes from the small scale. Lyman-alpha is also complicated because the large scale, because of that distortion they are talking about, we lose the large scale. So essentially, when we fit the continuum in each forest, what you're doing is you're taking whatever density mode is there of the size of the forest and setting it to 0. And we have a range of forest lengths. And that means you have a complicated, so in the power spectrum, what you would see is the large scale just going to 0 exponentially at some k. So you're basically losing that information. So it's not clear. We haven't really looked at how those large scales, like how that cosmology is lost and in what way. But that's definitely something. That's what I was saying at the beginning. If anyone wants to work on the continuum, it's one of our main problems.
But I had a question about that.
Yeah.
So I think there was this paper in 2018 by Fred Davies where he did a PCA analysis on like a few thousand low redshift quasars to basically do a correlation between the red side. If you very accurately fit the red side, you can pick the blue side. Yeah. And then extend the low redshift result to high redshift quasars. Yeah. So why exactly hasn't that? Because I used that technique to measure quasar lifetime, and it worked really well because at this point they understand very well how to understand the uncertainties that come from extrapolating red sides to blue side. So what's the problem with using that for cosmology?
So we have used it in the past. The first few iterations of the Box analysis actually used a few different methods to do the continuum, and one of them was the PTA. And back then, so the problem is the correlation is not perfect between the red side and the blue side. So back then, at least, there was still some distortion that you would get, and whatever you get any distortion, you can't do cosmology. You have to model that distortion, even if it's not too much. So it's better to have more distortion that you know how to model than have a little bit of distortion that you don't know how to model, right? So by distortion, I mean the correlation gets shifted in non-trivial ways, right? It's not in the same place. So your model completely fails to fit anything at all, right? You could probably still fit BAO because you can just fit some polynomials. You don't care about the physics, but anything else would be just lost. And that means, but again, as far as I know, nobody has looked at this recently. So I don't know if recent advancements in that field would actually help us. That's something interesting.
Well, there is
yes, yes.
Working on doing something similar with machine learning techniques.
Okay.
Correlation to see, but the goal is to try to have no distortion at all. Just as they were saying, if you have some distortion, then you need to model it, or otherwise the information is lost.
Yeah.
So it's better to have like more distortion, but actually control than just a tiny bit of control.
Yeah. So let me skip this because I'm running out of time. Yeah, just quickly wanted to show you also. So I was showing you before the forecast for Lyman-alpha BAO, and this is showing what we could do if we also measure Alcock-Paczynski from the full shape and that's what I'm currently working on. Will further improve the result, the constraint quite a lot. So the final thing I want to quickly talk about is also redshift space distortion. And this is basically the flagship for full shape analysis with galaxies. Mostly people talk about redshift space distortion. Obviously, there's also Alcock-Paczynski effect, but that's what people focus on. And that's because you can measure the growth rate through that. So this was the picture before, and this is what we have now. So we've done this measurement, and with that, we hope to do what's being done with galaxies as well, which is measure Alcock-Paczynski and redshift space distortion as well. And obviously, once we do that, there's also the possibility to do what we call a high redshift 3x2 point analysis, where we combine all these three correlation functions into one of these full shape analyses. And this would be very helpful because it would help you break degeneracies between all of the nuisance parameters like biases and the parameters that control the contaminants and so on, and help you get much better constraints of the cosmology. So why this has been really tough with Lyman-alpha and we can't do it is because this is just showing how we model linear theory of Lyman-alpha. You have an isotropic linear power spectrum template, and then you have this Kaiser curve that has some bias, and then usually for galaxies here, the quasar also showing is you have this F, the growth rate, and if you have bias and F, you can measure both of them. So this controls basically we set it isotropically, and this gives you some anisotropy, but it's different anisotropy compared to Alcock-Paczynski. You can actually tell them apart. However, as you can see for Lyman-alpha, you have this extra pesky bias, velocity divergence bias, that you can't really, we don't know it, so and it multiplies or adds, so they're completely degenerate with each other, and that means we can't measure the growth rate of Lyman-alpha. However, if you look at this equation, the cross correlation not containing the quasar we have alone. So if you can use the autocorrelation, measure this first term, then you could measure the growth rate just from the quasars in the cross correlation. So that's the first thing that we want to do with that in order to get some growth rate constraint from Lyman-alpha as well. And this is showing just the forecast of that. It's Alcock-Paczynski versus Lyman-alpha. So we're actually measuring the product of this growth rate times the amplitude of structure in spheres of 8 megaparsec. And you can see here that Lyman-alpha in terms of Alcock-Paczynski is much better, much more information compared to the quasar auto. And that's easy to understand. In the quasar autocorrelation, each spectrum gives you one data point. That's the position of the quasar. For Lyman-alpha, each spectrum that you take gives you hundreds of data points because you have in each forest, you have hundreds of pixels. So that means you have a lot more information in Lyman-alpha. And for Alcock-Paczynski, it's very clear that you get more information. But you see for sigma-8, because the information just comes from the quasars and the cross, the improvement is sadly not as good. But it's still an improvement. So, and it hasn't been done before. So this is something that we want to do in the near future with that. And this is just showing the growth forecast. Sorry, not the forecast, the measurement from the growth. In this case, it's not just eBOSS and BOSS. It's a bit of a few of the other data points that you can see. But the point here is that you see they're all measurements at low redshift, and there's no measurement here at high redshift. And here I'm showing the forecast for our Lyman-alpha plus cross combined, the quasar auto, and then all three combining high redshift 3x4. So that's the hope for that. And that's my summary slide. And thank you very much.
Well, we've got a section of questions, but maybe someone has like some final questions for Andrei. Maybe in Zoom with us, or I don't know.
I can't see Zoom.
No, I don't have any question. Thank you.
Okay, so then, yeah.
I think I heard something.
No, I said I don't have any question. Thank you.
Cool, great.
What's happening with DLAs?
Right. I think Ignacy actually is way better at answering this, because he just published a paper on that. So
yeah, so yeah, we're trying to like split the DLAs, but not only DLAs, but also other absorption from circumgalactic medium absorptions. So we want to split it from the regular Lyman-alpha. And if we do that, it's surprisingly we find that we're not losing much constraining power in the Lyman-alpha autocorrelation itself. But then we put things back together and we do like a joint fit with, instead of 2 correlation functions, we do 3 types of correlation functions, then we can gain like 8% of improvement. So I guess the plan in there is to try to understand some problems associated with the metal, because these systems are where most of the metal live. And then it seems that there is some issues with the metal modeling when you go to these kind of more metal-rich systems. So we'll need to revisit the metal model. But in principle, if we manage, if we can include those, then that could help us, even with break a little bit more of the generosity given that.
So right now, in this case, we're just masking the DLAs that we can detect, and then we have a model for the smaller DLAs in order to account for their effect. But I think the problem is we have many different types of correlation. So this result were with 4 correlations. There's the Lyman-alpha in Lyman-alpha region, autocorrelation crossed between Lyman-alpha and Lyman-beta region, and then both of these regions correlated with quasars. And that because in eBOSS, there was a lot of effort over many years to go take those correlations one by one and understand all of the effects. And we'll have to do that again with DESI. So I think the DLA cross correlations are the 5th or 6th, something like that. We have many, and the problem is the more you add, the smaller the improvement. So it's really the Lyman-alpha autocorrelation and the cross, the main ones are where we gain most of our signal, and that's where we start with. And actually now with the early data, we only have those 2, and then slowly we'll add more and more. And by the end of DESI, we don't know how many we'll have.
Yeah. So the point is that the other, you gain more knowledge more on the astrophysics part rather than cosmology, because you're focusing more on small scale metal contamination, like actually gas physics. But this could help us in the long run if we want to use the entire correlation function. But that doesn't mean that necessarily it's going to be helping us add much to the VAO. just basically we're measuring the same thing, right? Okay. Any more questions? Not.
I think we should thank him again.
Yeah. Then,
Thank you for having me.
and let's try to.
I don't want